Hello everyone, welcome back. So today we are focusing on advanced regression techniques. So in the previous videos we have already covered the simple linear regression and the multiple linear regression, and it is advised to go through those presentations before coming on to this one, because the basics covered in those two presentations or the explanations will be handy and will be mandatory to understand the concepts covered in this explanation of advanced regression techniques. So what will this presentation or what will this explanation cover? Firstly, so in real life, the data may not be that linear. So in the previous explanations, we have seen that there is a linear correlation between the available data from real life, and this is where we start working on the linear regression. We apply linear regression techniques, but it not be as linear. It may not be a straightforward relationship in real life. So how do we deal with that non-linear data? And then apply these regression techniques on non-linear data. So this is why the regression techniques are so prevalent in real life and use cases, because it takes care of non-linearity. And how it does that, we will see that. So for that, there is a technique called regularization. We will understand what is the concept of regularization, what is the intuition behind it, and how it is applied. And using the concept of regularization, we arrive at two techniques of regression, of advanced regression techniques, which are ridge and lasso regression. And then we will use a graphical representation to, we will see how graphically we can better understand ridge and lasso, in addition to the mathematics behind it. So that important takeaways and some key points while implementing these advanced regression techniques in real life. So starting off, how do we identify nonlinearity in data? So the first thing that comes to the mind is simply plotting a graph and see that there is a pattern which is not essentially linear in nature, just like this. And in such, there are for regression we seen that there are certain assumptions. So the error term or the error term, that is the difference between the actual and the predicted, should fulfill certain conditions for regression to hold. So this is one check that we need to do before moving on to the advanced regression techniques. So these are the assumptions. Basically, this is what we need to check. The residuals are to be scattered randomly around zero. The spread of residuals is fairly constant, and there are no extreme points or no extreme outliers in the error terms on the differences. So, if nonlinearity is seen, each predictor against residuals may be plotted to identify which predictor is nonlinearly related to response variables. So, for example, so there are variables x1, x2, x3, which predict a target variable y. So now we see that there is non-linearity. The real life data points are spread in a pattern which is not linear in nature. So we can use one independent and one target, or the dependent variable uh, taking a pair at a time and understanding what kind of relationship actually exists. So how do we handle this non-linearity? So these are the three techniques by using which we can handle nonlinear data and apply these regression techniques to make a prediction. So polynomial regression is one, transforming the data into usable form on which regression can be applied is another, and the third is using nonlinear regression. So see how a regression is can be applied widely over the real life data. So starting off, the first one was polynomial regression. So in real life, we see that there might be some regular shape. This might be some pattern which is not linear in nature, but it is actually a defined shape in which data is scattered across. So we saw that in a simple line equation, y is equal to beta naught plus beta 1 x. In that case, this was a simple line. We got a graph in the form of simple line, which had a coefficient of beta naught, which was the intercept to the y-axis, and the slope b beta 1, that is the slope of this line. Then in case of a higher degree equations, so a polynomial model would have a degree higher than 1. It could have a degree of 2. So for example, in this case, this is a quadratic equation, or this is a polynomial equation of degree 2. So 2 being the highest coefficient, highest power of x available here. So that it could be a cube, it could be to the power of 4 or 5 and so on. It could be an nth degree polynomial basically. So this is how the real life data would could come to us. It could be a polynomial with degree 3 also, where x to the power of 3 is the highest degree term right here. So now we see that it can still be expressed as a linear regression model. We still can form a rough relationship between y, the target to be predicted, and x, the independent variables. So this could be the relationship right here, which is say not linear in nature essentially, but can have a polynomial kind of relationship, can be expressed through higher powers of x rather than just power of 1. The other technique is data transformation. So the data that we have, since we see that it may not be linear in nature, it may not be a direct linear relationship, we we examine the data by taking one pair at a time, by taking one independent variable and one dependent or the target variable, taking two at a time, and see that there is some relationship which is not linear, and it could be these kind of relationships. So it could be a logarithmic relationship, it could be a square root function, it could be 1 by y, the inverse function, or some other function. So we simply by examining the graph, examining the trend that we see from the scatter plot, we might be able to figure out that there is an exponential or a logarithmic or some other function at play here, and those can be incorporated in our regression equation. But then again, as we said that the residual, the difference between the predicted and actual, needs to be checked for random distribution and normalcy. And transformation is more of a trial and error approach. So you could sense that it is a logarithmic relationship, but it may not fit that way exactly. So it is more of a trial and error method. So the third one was using a non-linear regression, and this is the most important or the most widely used regression method. So as we saw that the relationship was, it could be a polynomial equation of with nth degree of x, or it could be some other relationship defined by logarithmic or an exponential relationship with some of the variables. And then the third possibility could be a different relationship altogether, having these two constants who will define the relationship, and the x could be uh, to the coefficient could be raised to the power x, and this could roughly define the function or the equation that we have in real life. It could take any of these forms. So this is another kind of regression that we can use in our machine learning models and to come up with the predictions. But again, in these, as it is mentioned here, in these relationships, in the simple linear regression, we saw that the residual sum of squares was the cost function or the RSS. It is minimized to find out the conditions where we get the optimum fitting line. But how we got those conditions? What it was a quadratic function. So a quadratic function has a global minimum per se. So we saw that this is what a cost function looked like in that case, and we found out this point, the conditions of beta naught and beta 1, the values of beta naught and beta 1, which would give us this point, the global minima. So this is what we found out in the simple linear regression, which will not be the case in this. So there would be some other techniques some of which we'll be studying here and some in the next upcoming videos, using which that optimum solution is reached at, or the best fit graph or the best fit mathematical function is arrived at. So revisiting that, this was a quadratic equation. We had the residual sum of squares. The sum of this entire thing was to be minimized to find the set of conditions where the slope or the coefficient, the two coefficients, slope and the intercept, we were able to find that best fit line. So we had a global minima in that case, linear equation, but that will not be the case in advanced regression techniques. So how we did it? We differentiated the RSS equation with respect to beta naught and beta 1 equated to 0. This has all been covered in the previous explanation. So this is how the graph of this is how the quadratic function of residual sum of squares or the cost function looks like, and we needed to find the minima of this to get the conditions where we would get the best fit line of linear regression. So now there is a new term for advanced linear regression techniques called regularization. So what is it, why is it needed, and how it is applied will be covered in the upcoming slides. So So what happens is any model, any machine learning model that we are working on, it learns patterns from the existing data. So what we do is it is expected here that you know that if for applying any algorithm in machine learning, we split the data into trained data and test data set. So we used say 60-40 or a 70-30 kind of ratio, wherein the 60% or the 70% data is for training purpose, that is for the machine or the algorithm for the model to learn the relationships from the existing data, and then the relationships that are learned by the machine are tested on the test data for accuracy and whether it can be generalized and used on a universal level if we have a model which can make the predictions. So now there would be cases when the trained data is learned too well by the machine, and that case is called overfitting. And when overfitting happens, we see that there is a low bias, which means the difference between the the uh, the existing sum of squares of residual, or the difference between the error terms, or the sum of square of error terms, or the difference between the actual and the predicted value is very less or nearly zero. So we see that it is a case of low bias, but there is a high possibility wherever we have a very low bias situation, there is a high variance situation. So high variance would mean when we use that relationship that we learned from the training data into the test data, we see that there is a big difference between the actual and the predicted values. And similarly, there are situations which we call it as underfitting, wherein we will get high bias and low variance, and we might get low variance or high variance, but the bias is high, which means the existing data basis which the machine is learning, even in that there is a huge inaccuracy, there is error, and the machine has not learned from that data to make the predictions. So now we want to have a balance between bias and variance. And if we get an overfitted model which learns on the training data too well, it is more likely that it will be complex because it will try to cover every aspect. It will try to give equal importance to every feature or the entire data set that we have, and it will be a complex model which will not be able to interpret that well or explain it to the end to the business or the end user. So the model complexity will depend on the number of coefficients. So if we have say 100 features, 100 independent variables and one dependent variable whose value we need to determine from the 100 independent variables, the model will be complex if we are using all the coefficients, all the features in making that prediction. There might be some features which may not be that important, relevant, or there might be some features which are redundant. So our model need to take care of these things, that the redundancy or the not, not less relevance of certain feature to make a prediction. We need to have a simpler model which does not take all of the data, everything into account to make the prediction. We need a simpler model. So regularization is a technique which penalizes the cost function to be minimized. So the cost function, that is RSS, it needs to be penalized if we have a large number of features that we are going to include in our model. So what happens is we add a penalty term to the cost function, which we'll see in the next slide. And then that penalty term, cost function is RSS, we add a penalty term, and this penalty term will govern how we reach at the optimum solution or the optimum set of conditions. So it will be clear in the upcoming slides with the graphical and mathematical explanation. So the penalty term consists of two parts. One is the value which contains the slope values, or the say, for example, if we have x equal to beta naught plus beta 1 x1, beta 2 x2, beta 3 x3, something like that. So the beta 1, beta 2, beta 3 are the basically the coefficients, and the slope of these features, or we can also say the slope of these features. So say in simple linear regression we had beta 1, which was the slope of a simple linear line. In a higher degree or a higher number of features, a multiple linear regression scenario, we will have large number of features, and each one would have a coefficient which would be the slope value. So the penalty term will have a slope value and its own coefficient, which we know by the notation of lambda. So these two define the penalty term. And the idea is using this part, the RSS plus penalty, we shrink the coefficients towards zero. So when the coefficients are getting shrunk, we see that lesser features are lesser number of independent variables are relevant to take into the account in the final model. So now moving on from theoretical explanation into the graphical part. So say if the data is something like this, these are the points actually available. So if we have a model which goes like this, a blue line, this is the blue line, which goes like this. This is missing out the point that there is a change in shape. This model is missing out that point. It's a bad fit. But then if this blue line moves, or the red line, beg your pardon, or the red line moves in tandem with the blue line. The blue line is the actual and the red is the model that we are trying to come up with. And if it replicates this, it is a good fit. Now there is a risk that this good fit is too good a fit and every point is covered. And this is why regularization is used to reach at a compromise wherein we are having a model which is not exactly fitting on the trained data, and as a result not losing its relevance on test data. It is relevant on test data also. So now what is regularization and how does it help this problem of overfitting and underfitting? So in the previous slide we saw that regularization is introduction of penalty term in the RSS, in the cost function. It penalizes the model for having a large number of features, and thus it discourages from the model from becoming too complex. So this is what we were talking about bias and variance. So if the error term, so if we have a very good model, if we have a model which has understood the initial the trained data very well, the error would be low. The error would be low, but again, what happens is the variance or the difference or the error terms in the training data will go high. So if the model is very less complex, so if we are here, if the model is very less complex, we have not taken into account too many features or the optimum number of features, then the bias will be high. So which means that the model is underfitting. It is not able to, it is not taking into account the features. And similarly, if the model complexity is too high, we see that the bias is low, which means the difference between the actual and the predicted value in the training data set is low. There is a low bias. But then if the model has learned the training data too well, the variance will be high. The variance is calculated from the test data. So either case, if we are at this portion or this portion, we are having a very high total error term, which is not giving us a good model. We need to be somewhere here, and we need to find out this sweet spot between bias and variance, where we'll have the total error will be less. So in what we did in RSS, so what RSS did was, what RSS did was, we found out this global minimum. This is the RSS. This is the function RSS and this is the slope. So what happened was, we using differentiation of RSS, we differentiated this equation and found out this global minima, which gave us the value of slope at which we got the best fit line which is closest to the data, which can predict uh, from the data the best, which will give the minimum residual sum of squares. The sum of squares of these points will be the minimum. So this is what was happening in simple linear equation. So now what, just taking this, the concept into account, what is happening here is that now we have to reach this point, total error needs to be minimized. So we are, what we were doing here was we were trying to reach at the beta naught beta 1 by using cost function. We were using the optimum beta naught and beta 1, which would give the best fit line. And here, now we are targeting that this should be minimum, the total error should be minimum. So if we have to reach the total error to be minimum, we have to s- tune certain parameters in order to reach here. Here we tuned the beta, we differentiated this line and we got the beta beta. Now we have to get the minimum error. So how do we get that minimum error is by compromising between the bias and the variance. So we have to do hidden trials, or we have to optimize, or we have to do a hyper parameter tuning is the term actually used. So we have to tune that penalty term, which is lambda, into the slope part. So we will see in the upcoming slide how this slope is taken in ridge and lasso regression. These are the two techniques which we will cover. So in these two techniques, the slope is represented in different ways, and this penalty term, this entire penalty term, is helps us to using this the RSS plus the penalty term, which is the new cost function now. Now we'll work on this part, this entire portion. We will work on this to arrive at this lowest total error, and this will be obtained at a certain lambda. So we are trying to find out which lambda gives us the least total error. This is what is going to happen in regularization, or more specifically in ridge and lasso. So, uh, how, so this is how it is. The L2 regularization. So, ridge regression is also known as L2 regularization. This is the terminology which is going to come up in the advanced regression techniques. It uses a penalty term having squares of slope coefficients of features. So, this part, which was beta naught, beta 1, beta 2, which are the coefficients of x1, x2, and so on. So, this part here will be the squares of the slope will be taken, and in L1 regularization, which is the lasso regression, we use the absolute values of slope of coefficient. So this will be covered in the next two slides, how L2 and L1, that is ridge and lasso, work. So just in the last slide, we saw how we are doing hyper parameter tuning to set lambda to optimum value, which will give us the least total error. This is what we are targeting to do in these two regularization techniques of ridge and lasso. So ridge regression, now this is the formula that is used. This is the penalty term. This entire part is the penalty term, and this is the uh, this again will have two components. So this is L2 penalty term inserted in the end of RSS function. We already know that this was the RSS function. Now we are inserting the L2 penalty term on it, and this lambda is the hyperparameter which we are going to tune, or which we are going to check, which will the particular lambda which will give us the least total error. This is what we are targeting in ridge regression. And again, this b square, the summation is again the sum of squares of the coefficients of different independent variables x1, x2, x3, and so on up to xn. So these are the coefficients. This is the sum of squares of coefficients. Now we see that what is happening from this equation. So this becomes a new cost function, and in this new cost function, we are taking into account all the slopes of the different independent variables. Now, by manipulating these slopes, we will see that which of the slope, or which of the coefficient beta 1, beta 2, beta 3 out of beta n will be more relevant. These values will be using the what ridge regression does is it shrinks these value close to zero. Some of them will actually get to zero in lasso regression, but in ridge regression, this technique will bring these all these value close to zero. And this is how we will get the relevance of which features are important and which is not. And this is how we will penalize the presence of extra features. So as an example, we see that again, these are different lambdas. Hope it is visible in the screen. This is lambda. This is a case of overfitting when we are taking lambda equal to zero. So if here lambda is zero, this is nothing but the same. Sum of squares of residual. There is no change. And in this case, we see that there is a chance of overfitting. We are actually experiencing that the model is overfitting or overlearning the existing data, the training data. But then if we see that lambda moves from 0 to 0.1, there is a remarkable improvement in the model or the prediction model that we are trying to come at. And if we move it to 1, if the lambda now moves to 1, if the lambda further increases, we are further penalizing. This loses that sweet spot, and then again the shape of the graph changes. And at lambda 10, it further changes, and now it becomes a case of underfitting when the model is giving errors or which is giving a very less accuracy for even the training data. So higher lambda means over regularized model, which is this case, leading to underfitting. So now what a ridge regression does is it includes all the predictors in the final model. So uh, these values, the coefficients, will not be equal to zero. They will decrease, and they will approach zero, but not equal to zero. So what will happen is that we might have same number of features, even though this model has penalized the presence of additional features by reducing these values, by shrinking these values close to zero. But it is still a complicated model which will have a large number of features. So this is an example. This is an output screen of a Jupyter notebook where these two techniques were run on a similar data, the rich and lasso regression techniques, and we saw that the R2 score for in each of the cases we had the same polynomial regression of degree 5, and the lambda was changed. So as we were talking about the hyperparameter lambda, we had to tune this lambda and we had to find that lambda which will give us the best fit line. So this is what is happening. If we had lambda 1, it will be a huge difference. R2 score is 0. Then again, even at 10 lambda, we are again missing the point, missing the spot by a large margin. Now, if we decrease the lambda to 0.01, now we are moving closer to the existing data, and we are getting an R square score of 95.9%. And further decreasing lambda to 0.001, now we are hyperparameter. This lambda hyperparameter is being tuned to 0.001. We are doing a hit and trial, and we see that at 0.001 we are getting the best R2 score, R square score, which is 98.26%. And this will give us the best lambda and hence the best model. So this is how by optimizing or by trying out the ranges of lambda, we understand which lambda will give us the best fit graph. And as we saw in that ridge regression equation, this is the lasso regression equation. Everything is same. The only difference is that instead of using beta square, the sum of beta squares, we are using doing summation of absolute values of beta. The squared effect is going from here, and this will help us to actually get the coefficients which are non-relevant as zero instead of getting values which are close to zero. The detailed mathematics is out of scope of this explanation, but this is broadly how ridge and lasso regression work. So lasso actually shrinks the coefficient to zero, and by doing that, some of the features get eliminated, and hence the model selection, the feature selection is actually done in the model, and model becomes easier to interpret. And as we saw from the bias variance balance, this was the total error. So we get the value of at a certain lambda, we get this minimum total error. This is what we are doing. So now how does it work? Now this will be a graphical intuition how things move. So now initially we saw that this is the sum of squared of errors and these are slope values. So for a simple equation, say a simple linear equation, for slope values, say beta 1 was the slope values and this was the RSS function. We saw that this was a quadratic function. It moved like this. And this is what it says. So this is the quadratic function. The slope value is the beta 1 in a simple linear regression. And this is for the sake of understanding, we are just thinking about beta 1 and not the other coefficients. So what L2 regularization or the ridge regularization does is at different lambdas. So what we are here, instead of RSS, we have this entire cost function has now changed. We have added lambda into slope square, which is a penalty term. This will define the penalty in total, and lambda will be the severity, will decide the severity of the penalty, how severe this penalty will be. This is given by lambda. Pardon me for the handwriting because I'm using a mouse. So what is happening here is at different lambda, we see that when lambda increases, the minimum point, this is the ultimate goal that we have to get. We have to get that global minima. So this global minima has shifted from here to here. So there is a shift of global minima. But again, even at a very high, freakishly high lambda, we see that it is still not zero. And if we had this value at 0, then it would have helped us do some feature selection. We would have dropped those features where we would have gotten this kind of graph where we would have this 0 slope. So this is the decrease that is happening with increasing lambda. We are getting closer to 0. This is the beta 1 value or beta I value for any ith beta. And what L1 regularization does, or the Lasso regularization does, using that absolute slope term formula and minimizing that entire cost function, we find that when lambda gets high, we are actually moving from here to here, which is actually 0. So our slope value has actually reached 0, and this has helped us do feature selection, and we can, wherever at a certain lambda we can get that 0 value, we can drop those features and we have a simpler model. This is how regularization, both ridge and lasso, work. So now this particular slide will cover the output screen of a particular use case wherein both ridge and lasso techniques were applied on the same polynomial. So what is noteworthy here in this slide is that Lasso is actually helping us getting to 0 coefficient values. So these are the coefficient values of variables x2, x4 and x5. So when we have these values reach 0, in Lasso we will drop these features and our model will only take into account x and x3. So this is just for the sake of understanding. Another, while evaluating, when we build that model, we evaluate this model using these. This was for the sake of understanding how Lasso will help us do the feature selection, and this is how we will actually evaluate our model, and we can compare these techniques, what kind of output we were getting. So what is happening here is we saw that for a regression R2 square is the standard measure, is the most commonly used measure for understanding how good that regression model is. We see that this in simple linear regression we had actually 0.975 yeah, 97.5% of the value of R square, which in case of test data reduced to 83 from 97. So there is a huge drop, which means this was a case of overfitting. Now, what happened is when we applied ridge regression, we saw that this difference has decreased, and we are getting a reasonably good R square when we are applying ridge regression by using L2 regularization, by using ridge regression. And if we use L1 regularization, that is lasso regression, this is what we are getting. So we see that there is still there is a slightly better outcome by use of ridge regression. So now the question comes is where to use ridge regression and where to use lasso regression. So this will be covered now. So to start with, we saw that regularization coefficients are shrunk towards zero and towards each other by shrinking them towards zero actually. So, but when this happens, we know that the actual real data in the use cases we see that they may not have the same scale. Some values may be in millions, some could be in tens. So, shrinking them, weighing them on the same scale, shrinking them using similar technique may not give us a very good result because shrinking a million to by a certain percentage by a certain method and using that same way of shrinking value which is in tens 10 to power 6 or will not will give us the coefficients that we are getting the coefficients which are being shrunk say beta 2 and beta 3 what we are trying to arrive at we are trying to arrive at beta 2 and beta 3 now this will still be higher so we need to have these independent variables at the same scale. So we want them to be centered and scaled in order to have a variance of 1. And that is when, and this is a mandatory condition for the advanced regression techniques, Ridge and Lasso, to be effective. So now how will we choose between Ridge and Lasso? So as we saw that if a data set, in case of ridge regression, what ridge regression does is it basically retains most of the features. It does not drop many features because it uh, it converges the coefficient value towards zero but not equal to zero. So it will help us retain all the features. And we see that there are many correlated features, and dropping the features will help us, will actually cause the model to lose its efficacy. So we want most of the features to be carried forward in the final model. That is where we will reach. We will use ridge regression. Now, if in the use case we see that only some of the features are actually truly important for our prediction and there is some redundancy, Lasso would be a good choice in that case. Thirdly, interpretability. If interpretability is an issue wherein we cannot afford to have too many features, then again Lasso regression will help us get a better model. Ultimately, whatever technique we use, ridge or lasso, there's a certain technique called cross validation technique, which is actually the hyperparameter tuning part. How lambda is tuned by cross validating. This will be covered in the upcoming explanation. So cross validation technique is basically a hyperparameter tuning technique for getting the optimal lambda, which would help us get the lowest total error, as we saw that in the bias variance uh, explanation. This was the total error part was the minimum at a certain lambda. So these cross validation techniques will help us get that lambda, which will help us get the lowest total error. So this is how the advanced techniques work, and see you in the next explanation covering the regression, more some of more facets of regression. Thank you.